Well, I'm speaking on behalf of the ERNI Spanish Embedded community. We are a group of folks who are passionate about the technology. This year, we are trying to organize a tech talk every month. So stay tuned and subscribe in both Eventbrite and Twitch, so you don't miss the upcoming seasons. Today topics is Rust. So I have the pleasure to welcoming Jose Ramon Alvarez Rojo, who will be in charge of this season. He is one of the most active member on board the community. He has master degree in telecommunication engineering, has successfully contributed to several projects at ERNI, as well as some personal project as an entrepreneur. I'm not going to expand any further and leave it to Jose Ramon to take over.
Yes, please.
Enjoy the talk.
Thank you, Gonzalo. Yes, please don't expand it any further because it's such an impressive introduction. Thank you very much. Well, welcome to this ERNI Academy Twitch session. This session is about Rust programming language, brought to you by the ERNI embedded community. So please let's give some minutes maybe for more people to connect, and in some seconds let's dive in the world of Rust programming language. Okay, let's go. Yes, well, Rust programming language. This is an introduction to Rust programming language, a brief approach on how to enhance the safety of your projects. This sounds very grandiloquent. Well, let's talk a bit about the history of Rust. Rust programming language started in 2006 as a side project of Graydon Hoare, who was working at Mozilla. Later, Mozilla decided to sponsor the project in 2009, and in 2015, Amazon, Google, Facebook, and Microsoft declared to use it in I don't know what project, honestly. But in 2020, wave of layoffs happened in Mozilla, and that led to the creation of the Rust Foundation. Keep an eye on that foundation because it is an alliance between Amazon, Huawei, Google, Microsoft, and Mozilla. The same year, in 2020, Rust reaches the top 20 position in the TIOB index. That, as you know, is an index that measures the interest of the development community on programming language. 2022 is the big milestone year. The Linux kernel development team decided to include Rust along C11 and assembly as the only languages that can be used for the development of the Linux kernel. So there are currently 3 languages allowed to be used for the development of the Linux kernel, which are assembly, C11, and Rust. In 2023, the National Security Agency publishes a statement about memory safe languages, and this is a list that includes Rust among Python, Java, C#, Go, some others, and of course Ada as programming languages to be considered memory safe. So this is another big milestone. And recently, some weeks ago, the United States White House Office of the National Cyber Director published a paper urging all programmers to start using memory-safe programming languages. And some days ago, Google gave away $1 million to the Rust Foundation to support improvement of the interoperability of Rust with existing legacy C++ code bases. So here we can see a clear strategy on decrease the production of new C++ code, which is considered as memory unsafe, and start the creation of new programs written in Rust and leverage the existing C++ code by means of interoperability. That interoperability, we are going to cover it later in this session. Meanwhile, the Stack Overflow community has chosen for 5 years in a row Rust to be the most loved language, but in the real world still the number of positions offered in LinkedIn for Rust is like 4 orders of magnitude smaller than the positions for Java and C++, which are the most demanded languages nowadays. Well, then why is Rust awesome? Well, we have Cargo, which is a Swiss Army knife tool, a super tool including a package manager, a build system, a test runner, a linter, docs generator. The package manager is cool because you only have to write a dependency list and it goes to a repository and fetches the dependencies for you. The build system is would be something like CMake equivalent. The test runner will be like similar to Google test, and we have also a linter which is called Clippy, and the docs, which are very important in the Rust community. Of course, the flagship of Rust is the memory safety. We use safe by default, the ownership mechanism and lifetimes to manage the memory, which gives that safety everybody talks about. Rust offers us fearless concurrency in the sense that no data races can be given in your code. It is impossible that for a program with data races to compile. It won't even compile. This is not the same as a race condition. That by data race I mean the unsynchronized access to shared memory, and that's what Rust prevent to happen. And of course the books. We have lots of books. We have the Rust programming language book. All of those are for free, and you can use the Rust programming language to learn how to program in Rust. You can consult the Rust preference. The embedded Rust book is devoted to the development of embedded applications. You can learn Rust by example, and for those with that can go deep in the register level and who wants to do dirty things, we have the dark arts of unsafe Rust, the Rustonomicon. Let's see now how does Rust compare to other languages. Usually we have a trade-off between control and performance and safety. Control and performance are in the same axis because usually the more control you have, the more low level you can go, and that potentially could give you more performance. And safety is safety means here the probability to have memory errors. So traditionally we have one edge with C and C++ that gives you full access down to register level, full control and potentially full performance, but no safety unless you do the things very well. And in the other edge we have Haskell, which is a super academic, very high level language, super safe, but you cannot go to register level with Haskell, at least not easily. And we have a lot of languages in the middle that try to balance this trade-off. But actually, there is no such a trade-off because we have two outliers here, Ada and Rust, that are both performant and memory safe. Ada has been traditionally used in aeronautics and mission critical software, and Rust is the newcomer here. Let's talk about of what I call inherent safety. We can have systems that are safe inherently, that is by default, and others that are not. If we have the problem of going from point A to point B, we can solve this problem by building a road and using a car. But the car can go off the road easily if we are not very keen driving. So let's put some guidances, some hints and helps. For example, let's draw a line to divide clearly between which lane is for each direction. We could put this white line on the edge so the driver can tell if he's approaching too much to the border of the road and can correct the course. We could also develop super complicated systems to assist the driver and even to take the control and avoid the car going off-road. And another option will be just build a railroad track. And the difference here is that we put here a lot of energy trying to turn the system safe. It was not safe at the beginning and we make it safe but putting in energy. But in the train case, if we wanted it to derail, we have to put energy. So by default, inherently, it's safe. Here we have a similar picture, and this is the approach that Rust has chosen. For example, down to code level, we see that values and references are immutable by default. If you want to declare a variable and mutate it, you should declare it as mutable, unless the compiler won't let you to mutate it, to change the value. We are going to get sane warnings with a good description of potential problems. We are going to have bound checked containers. We can't go out of bounds on an array in Rust unless we tell it explicitly to do. We cannot do it by accident. When we want to return, when we have a function that may return a value or not, for example, think about a hash map. You query a hash map and you can get maybe a value or maybe not if it is not contained. So if it's not contained, we are going to get a well-defined value which is called known in Rust language. And if we have some value, we are going to receive a sum from that function with the value encapsulated inside. So there is no need to develop meaning returning not well-defined value like -1, null pointer, or throw an exception. Speaking about exceptions, if a function finds an error, a condition, it should return an error. The function that have the possibility to return an error should return a result, and the result has two variants. If everything went well, we should return an OK with the value inside, or an error if it hasn't. And if we want to ignore all this and go unsafe, we must put all our unsafe code inside an unsafe block. We are going to cover that later, but the point here is the same as with the car and the railroad. Here we have to put energy to prevent the rock to smash the city, but here we must put energy if we want to provoke an accident. If we don't do nothing, by default this is safe. So as memory safety is one of the flagships of Rust, let's talk about a bit about some strategies that we can use towards attaining memory safety. Historically, one of the biggest causes of software bugs and security vulnerabilities has been accessing memory in an unsafe or incorrect manner. So we try to devise some strategies to try to lower the error rate. The first one is very obvious, is to pay attention and be very careful when we code. This is of course error prone, and it is affected by the IKEA effect. The IKEA effect is a psychological bias that humans have, which consists in putting more value in the things that we have done ourselves. So we tend to evaluate more the things that we have built. This strategy must be initiated by a human, and it's performed by a human, which is usually the same human that codes. That's why the IKEA effect appears. So if the problem is that the human is the same, we can introduce a new human to review the code of the coder. So we have the reviewer and the coder, and that's called peer review. This is good because Hawthorne effect arises. Hawthorne effect is a psychological effect, a change in our behavior. If we feel that we are observed, our behavior change, and this is positive in this case, because as we know that we are going to be reviewed, we put extra effort in writing our code without errors. But in the long term, it doesn't work, because the developer starts to trust the reviewer. If I know that I'm going to be reviewed by a very good reviewer, I can relax, because he or she will catch all my errors. And the reviewer can feel the opposite. If he or she feels that the coder is a very good developer, he can relax and say, okay, probably there are no errors because this person is very good coder, so no errors to review. And the problem is still the human part. We can decide to adhere to a standard. We decide to use a standard, a very well-defined rule set with very strict rules that everybody must follow and everybody knows. But the problem here is that it must be enforced and it must be checked. The compliancy of the standard must be checked, and the software must be certified. This must be initiated by a human. There must be a boss that decides which standard we are going to use and to enforce the usage of the standard. But it can be checked by a machine, but ultimately the seal of approval must be given by a human. We can use analyzers. We can use dynamic and static memory analyzers, and this is good because it's performed by a machine, has no biases, or shouldn't, but it must be initiated by a human, at least for the first time. And then we have another, these last three are different for the others in the sense that they are included in the language. They are more near to the code. So we have smart pointers like the ones in C++, which work very well if you remember to use them. They are automated, but still they have to be initiated by a human. But they are part, or almost part of the language. They are super near to the code. We have garbage collectors, as in Java and optionally in Python, that those are triggered and controlled by the machine, and the checks are performed by the machine, so we can rely on the machine. The human can force the garbage collector to kick in, but the problem is that in general it's unpredictable and the resource usage is very unpredictable. We see usually a peak in the CPU usage when the garbage collector kicks in, and that can ruin our performance. And finally, we have ownership. Ownership is the rules that Rust programming language follows, and those are part of the language. Those are the compiler is aware of them. So here we have both initiated and performed by the machine. The problem here is that we have a very steep learning curve. This is traditionally the learning curve of Rust that you can find in the internet, and we have here a big steep zone on the difficulty, and this is very discouraging because you have to go through this path just to make your code compile. But the reward is that if your code compile, it has a bigger chance to be error-free code. But in reality, you will feel like this when start to learn Rust. I'm not a Rust expert myself. I think I'm somewhere in this somewhere in this zone. But yes, I think this delusion path is what everybody feels the first months. Okay, let's talk a bit about memory safety. We have some mechanisms to manage memory, which at the end is the allocation and the allocation of values in memory. We have ownership, that is the responsibility on the responsibility of an scope on an in-memory value life cycle. The rules are these two. Values can have only one owner. So for each value there is one and only one owner. And with that owner, which is usually a scope, when a value gets out of scope, the value is dropped off memory following this order. If there is a destructor, the destructor will be called, then the part of the object in memory on the heap will be freed, and then the part on the stack. Okay, so we have ownership, but what if some other part of the code that is not the owner wants to work with a value? For that we have borrowing, which are references. References, unlike pointers in C++, and just like references in C++, must be always valid. And to guarantee that they are valid, we do lifetime checks, because lifetimes prevent dangling references. We don't want to dereference, to follow a reference to find that the value is not in memory anymore. That cannot happen, and we can use lifetimes to prevent that. So the code won't compile if the lifetime rules are not being followed. And the other borrowing rule is a very powerful one and a very strict rule that says that you can have either, for each value you can have either n immutable references or one mutable references. That is, you can borrow a value to be read from n places in the code, and for only one place if you want to write it. And you have to choose either. You cannot have one writer and n readers. And this is good because this is what prevents data races. Think that those places in the code are threads, so you can only have n reader threads and one writer threads, but not at the same time. So no data race is possible. You can have reader and writer threads at the same time, but if you synchronize them. What Rust guarantees that you don't have any unsynchronized access because the code won't compile. And of course, if we want to transfer ownership, we have move semantics. So if we don't have one object in our scope anymore, but we want other part of the code to control it, we can transfer the ownership. We are transferring the responsibility of deallocating it when it gets out of that new scope. Okay, maybe you remember the Heartbleed bug. It was a bug that was spotted like 12 years ago in the OpenSSL server implementation, and it went like this. This is a comic strip I like a lot, and it explains it very well. So we have the user mech talking with a server and asks the server to replay with the word bird, which is 4 letters long. I think that is like some kind of cryptographic challenge. The server thinks, okay, user mech wants this 4 letters bird, and replies with bird. But mech realizes that she can do this. She can ask for the word hat, which is 500 letters long. And the server takes the request and it replies with the word hat and the rest of the 497 words letters that include data about administrator and other users, and this is disclosing a lot of personal information. So let's have a quick look on how can we solve this in Rust. I have an oversimplified version of the Heartbleed bug and how can it be avoided from Rust. This is Rust Playground. It lets you to play with Rust code online on a browser. And if we try to run this code, the first error we see is that we missed the lifetimes. This is the lifetime check in action. We have here a struct with a reference to a string, and we must say that if this reference is going to live during a lifetime called A, the struct should also live for this lifetime. That is, the lifetime of the struct cannot be longer than the lifetime of the field it's referring to, because otherwise the reference set value could be wiped out and we will have a dangling reference. Okay, so we have solved this. Let's go through the code. We have 3 usernames. We create 3 user structs. We create a database and put usernames and personal data of the users. So let's try again. Whoops, non-exhaustive patterns. Okay, if you recall, it's a hash map, and when we try to get a value from a hash map, we can have some value or known value if it is not found. And in Rust, this is called a match pattern. It will be equivalent to a switch case, and we must cover all the logical possible cases. So we forgot here to put the case to cover the known case, which is the case where you query for a username and the user is not in the database. Here we choose to panic if we don't find that user, which will stop the program. And if we find it, we will simply print the username and the user data. This print function is like the one in the SSL server. I put the username and I put the length of the data for the user that I want to print. So let's try again. Borrow of moved value. Well, another classical error. Here we are moving the name of user 1 into a new owner, which is user 3, and this is not a copy, this is a move. This has move semantics because string is an object that lives both in the stack and in the heap, and we cannot easily copy it. So we cannot do what in other languages like Java is called a shallow copy. We must do a deep copy, cloning the object. And now this is a new object independent of this one, and we can bind it to user 3 without losing the ownership of user 1, because if we left it as is, we try to use here username, and user 1 name is not available anymore because we have moved it to user 3 name. So let's clone it, and that error should not appear. But we see here warning, yeah, unused variable user 3, and that's true. So let's remove it, and let's remove the clone also. No unused variables. Database is not initialized. We must initialize values in Rust. It's not possible to have initialized values. So let's initialize it to a default value. Okay, let's try again. Cannot borrow database as mutable. Of course, immutable by default. Here we are inserting user, that is, we are changing the database, but it's not mutable because we didn't put mute to indicate that this database can be mutated. And then, okay, we have here down below an unsafe implementation with unsafe code. We are taking a raw pointer. This is a dirty thing. It's a raw pointer without any check, and we are dereferencing it. This is unsafe, and we must to mark it as unsafe if we want to use it. Otherwise, the program won't compile. We are not able to run the program because no program exists. Finally, we have two warnings, but this is our standard output. And we have here MEX data 1, 2, 3, 4, 5, which is the data of user MEC, and this is standard output. This is standard error. The program has panicked. Why did this happen? Because we are trying to ask for more numbers that the user MEX has assigned. We are trying to go outbounds the array, and this is not allowed. And this is safe because it doesn't reveal the private data of other users. It panics before going further. If we used an unsafe version, the one which works with raw pointers, we don't get a panic, but we get MEX data along if the administrator data along a lot of things that are in memory. So that's why it's unsafe. We are revealing confidential information. Let's go back to the presentation. Well, let's talk a bit about multithreading. In Rust, since we spoke about it before, since you can only have one mutable reference or m immutables, data races won't happen, code won't compile. This is not true for race conditions. Race condition is an assumption you made on your code, for example, that a bunch of threads is going to run in a defined order, but in reality it does not happen, and the error is in your assumption, not in the code. You think that the logic of your program is one and it happens to be another completely different. Those are race conditions, but data races, which is the unsynchronized access to shared memory, Rust won't let you compile such a program. And if you want to synchronize it, you can use synchronization primitives like read-write logs, mutexes, atomic types. One cool thing about mutexes and logs, atomic types, is that they are containers. You don't have the unprotected value in one place and the mutex in other place. The protected value is enclosed inside the synchronization primitive, inside the mutex, inside the log. And the only way for you to access that value is through the mutex or through the log. This is similar to Java. Another option is not to share memory at all. Just make a copy and set it like a message. This is the approach that Erlang and Go takes, and Rust provides you a message passing framework following the philosophy of don't communicate by sharing memory, instead share memory by communicating. And there's also available the asynchronous programming. You can use async and await function, async and await keywords, like if you were programming in JavaScript, but this is not provided by default. The keywords are provided by default by the Rust language, but you must to take an external platform to do the scheduling of the task, and you have a lot of flavors. You have Actix, you have Tokyo, and so on, but those are external to the standard library. Well, since we are the embedded community, let's talk about how to make a Rust program run on a platform that is not a PC. We have a lot of supported architectures organized by tiers. There's tier 1, which is guaranteed to work with official support. And these architectures, you can use them both as target and as a development host. For the tier 2 architectures, they are guaranteed to build with official support, less quality control, and some of them can only be target. You cannot develop on them. And then there's tier 3 for the rest, without official support, where people do cool things like compiling for a Nintendo 3DS or a Sony Vita video console. You can find the full list in the official page. If we go down to register level, we start to work with microcontrollers and, for example, boards like ST Discovery boards. We have crates that give us support for those boards, and we can work with Cortex M microcontrollers. This is an example on the usage of the SysTick peripheral for a microcontroller, but here we cannot rely on the standard library because, for example, for if we want to have threads, we don't have the operating system providing thread for us because this is a bare metal platform, and we must to use, for example, a scheduler like FreeRTOS, which has a Rust wrapper for it, and or the real-time interrupt driving concurrency crate, which provides us the ability to run tasks and message patching and so on. About robot operating system, yes, the previous session by Diego Villegas was about robot operating system, and usually people use C++ to develop applications for ROS, but for the second version you can use Rust to develop your application for your little robots. Well, we talked before about interoperability in the strategy that probably is going to happen in the next 20 years about the switching from memory unsafe programs to memory safe. And that interoperability in Rust can be done by using the foreign function interface, which is an interface to communicate with other languages. Ideally, zero cost abstraction, no overhead, and everything should run as smooth as usual. If we want to call, for example, C code from Rust, it's very easy. We need to define an interface of the function that we want to use. Those are the signatures. This is very similar to a header file. We have the name of the function, the parameter it takes, and the return value, and we only have to provide the linker, the name of the library. So when we call here inside the unsafe block, when we call the C function, the linker will put here, will redirect the call to the C library. And the other way around, we can call Rust from C. We just need to build a Rust library and link it when we are building the C program. We need to declare the function as public to get access. We must to put this extern C to instruct the compiler in following the C calling convention, and we have to avoid the mangling of the name of the function so it can be easily linked. We must instruct cargo to compile not as an executable but as a library, and once we have the library, we link when we build our C project, we build against the library which is programmed in Rust. So let's see a bit of it.
We are 10 minutes left.
We have here an implementation of Conway's Game of Life. Game of Life is a simulation devised by the British mathematician John Conway, and it consists in a board full of squares, and the square can have two states. If the square is red, the cell is alive, and if it's black, the cell is unpopulated or dead. And every cell has neighbors around it, and those are the rules. If a cell is dead and it has exactly 3 neighbors, it will become alive. If a cell is alive and it has 2 or 3 neighbors, it will remain alive. And if a cell is alive and it has more than 3 neighbors, it will die of overpopulation, and less of 2 neighbors, it will die of underpopulation. I'm switching to the implementation here. As we mentioned, this is we didn't mention it. This is the architecture of the project. We have one user interface implemented in C++, and the business logic that is in C++ also, and I re-implemented it using Rust through the foreign function interface. So here you can see the interface of the business logic, and if we go to the Here we are declaring our Rust project to be built as a static library, and in the make file we will include it to be linked with our CPP code, and we can have a look to the Rust implementation. This is the cell state. Actually, a cell in this program can be alive, dead, or alive while calculating the next state, or dead while calculating the next state. And one cool thing in Rust is that in enum you can store a value. In this case, that value is the number of live neighbors. We can check the logic here, and if a cell is alive and we have less than 2 neighbors, it will die by underpopulation. More than 3 neighbors, it will die by overpopulation. Any other case which is marked by this underscore, the cell will live on. A dead cell will reproduce if it has exactly 3 neighbors, and otherwise it will remain dead. Let's switch back to the presentation, and well, this is an example of the simulation that you get when you run those simple rules. The fun thing is that with those very simple rules you get unexpected and very funny results, like this oscillator here. And I propose you a game for those of you in the chat. I will show you a cell pattern. Then you can write down in the chat the number of generations that you think that the pattern will live. That is, how many ticks of the simulation it will take until all the cells are died. And the player that makes the closer guess we will win glory and recognition and maybe a prize.
Jose, correct me if I'm wrong, but we will be doing one demo just to everybody
Oh yeah,
to know
yeah, to get a feeling
and
first.
get
Okay,
familiar with the game,
okay, let's get familiar
and
first.
then yeah,
Yeah, that's a good
yeah,
point.
then we will do the a second try where we will be um offering a surprise gift to the one who gets the number of ticks or be the closer one.
Yes, that makes sense. Let's have first a feeling of the game.
Okay,
Here you have
let's go for them.
the okay, thank you. This is a C++ executable, and this is the Rust executable. I'm using the Rust one, of course. And here, this simple pattern, when we run the simulator, we see how it evolves. This is called a glider, and it won't die. It will remain traveling forever. We can see here for each generation the number of live cells. The patterns can go super complicated, or some patterns are stable. I think this one is stable, can evolve to this. This is super fun also. This is a factory of gliders. If I try to evolve it, it will start to produce gliders until those gliders collide and destroy the factory. So maybe you can try to guess this one. Are we doing this for a prize, or maybe this do you want a first one for test, or well, let's go. Write down how many generations this pattern will live. Write down on the chat, please. Maybe 2, maybe 50. That's 15. 254. I have 7 minutes to go, so okay. Come on, write down your responses, your guesses. I can give you a hint. It's somewhere between 0 and 1000.
Okay, let's go. Let's go.
Let's go.
We want to
I'm
know.
launching it. Okay, current generation is 2, 44 remaining live cells. Advance it. Hey! This is the 10th generation, has only 4 live cells, and by the 11th generation all the cells were died. So congratulations, G. Matarrubia. Do we have time for another try?
I think so. Let's do another try.
Okay.
Yeah, before the real one.
No, this was the real one, or no? Okay, this is going to be the real one. Okay, this is the real one. This is for real.
Okay, okay.
I have no more patterns prepared, so this must be the real one. Okay, this innocent
Okay,
pattern.
people. Major bet.
You see, people, this innocent pattern. How many generations will it live before the total extinction? I can give you a hint. It is between 0 and 50. Okay, we have 2 guesses, 23, 30.
Come on, come on.
Shall I start?
Don't be afraid.
No more guesses? Come on, write down a number. You don't have nothing to lose.
Okay,
25.
25.
Thank you, San Escamo. Okay.
Let's
5,
see what
4,
happened.
3, 2, 1. Let's launch the simulation. 1, 2, 3, 4, 5, 6, 7, 8. It is evolving. It is evolving. It's dying. Whoop. I don't know if it is 33 or 34. So, congratulations, G. Matarrubia.
Yoo-hoo.
Well,
I have no idea. Believe me.
it was not prepared.
Okay, since my response doesn't count, I think the second closer response is from Sanes Camo.
Yeah,
So
congratulations, San Escamo. You have.
if you are
Let's check.
from Spain, that then you can send me your data, and we will send you a surprise gift. Well, it is not a surprise indeed. You have won a bottle of water, and
And
we keep the warm and cool for the temperature. Um, it's look oh, amazing. So
oh yeah, I can
congrats
show it. I
again.
can show it. Please show it to the.
Okay, okay,
I
okay.
forgot
Don't
to
worry.
switch the
No,
scene. Sorry.
no.
Is that super
Yes,
cool bottle of water for San
this
Escamo?
one or some similar, but yes. Send me a direct message with your data, and I will say in private which data we need to send you the gift.
And of course, glory and recognition. So, lot of glory and recognition for you, San Escamo. Well, so remember to better ask Ernie. Thank you very much for your attention. I hope that you had a good time with this introduction to Rust programming language. And see you later in the next session. Bye.
Well, thank you for your presentation, José Ramón, and thank you everybody who was watching. And see you in the next one. That I hope it will be a hybrid event in our office, at the new office that are coming, and will be available pretty soon, and also in Twitch. So
Okay.
thank you, José Ramón, and bye bye everyone.
See you.
See you in the next.
Bye.